Properties of waves. Here we have the coils of a slinky spring. The spring is being pulsed back and forth like this, and each of the coils would oscillate back and forth. It's called a longitudinal wave because the vibration is along the same direction as energy transfer. You'll see in places the coils are closer together or compressed. We call these compressions. In other places the coils are further apart or rare, and we call these rarefactions. To measure the wavelength of a wave, we need to find a point on one wave and measure the distance to an identical point on the next wave, from the centre of this compression to the centre of this compression, for example, as is shown here. Wavelength is always given the symbol lambda. We could equally have gone from the centre of this rarefaction to the centre of the next rarefaction. If we now consider this coil, if it is going to travel this far to the right and this far to the left, like this, as the wave passes, it has a maximum displacement to the right of this distance. Now, maximum displacement from the equilibrium position is known as amplitude and is marked here. So this is the amplitude of the wave. This again could be a slinky spring, but without the individual coils being shown. Now the spring is being pulsed up and down like this, with energy being transferred still in this direction. This is a transverse wave, trans meaning across, so the vibration is across the direction of energy transfer. Going from one point on a wave to the same point on the next wave, from this peak to this peak, gives us our wavelength lambda. Equally, from the centre of a trough to the centre of the next trough, or from the central line going down to the central line going down like this. Amplitude is still the maximum displacement from the equilibrium position, as is shown here. Now let's consider a wave as it moves like this. To consider this situation further, we need to introduce another term, the frequency of the wave. Now, frequency is the number of complete waves produced every second. A complete wave would be going up, down, and back to the centre, for example. Now, frequency is measured in hertz, which is abbreviated to capital H, lowercase z. 50 hertz would be 50 complete cycles every second, for example. Here I've marked a position on one of the waves and its starting point. If I allow the wave to progress for precisely 1 second, it has reached this point, and you'll see that 2 complete waves have been produced in that second. So the frequency of this wave is 2 hertz. Now, in 1 second, the marked point has moved 1 complete wavelength for every wave produced, and the number of waves produced every second is the frequency in hertz, in this case 2 hertz. We know that speed is equal to distance travelled divided by time taken, but in this case the distance travelled is the wavelength of the wave multiplied by the number of waves produced per second. So the wave speed is equal to the frequency in hertz multiplied by the wavelength. In symbols, wave speed is normally given the symbol c, frequency the symbol f, and of course wavelength the symbol lambda. So we get this equation, c equals f lambda. Now to look at a problem using that equation. If a radio station broadcasts at a frequency of 96.2 MHz What is the wavelength of the waves? Well, we're given the frequency of 96.2 megahertz, mega being 10 to the 6. So we can write it as f for frequency is equal to 96.2 times 10 to the 6 hertz. The wave speed, well, radio waves are electromagnetic radiation and therefore travel at the same speed as all electromagnetic radiation of 3 times 10 to the 8 meters per second. If we write our equation as lambda is equal to c over f, then putting in the numbers 3 times 10 to the 8 meters per second over 96.2 times 10 to the 6 hertz, we then get the answer of 3.1 meters. Intensity. Intensity is the rate at which a wave transports energy. It's linked to the amplitude of a wave, but as amplitudes go positive, negative, positive, and so on, they would give an average value of 0. If we square the amplitudes, the positive values stay positive, the negative values become positive, and so the amplitude squared is always positive, and we find that the intensity of the wave is directly proportional to the square of the amplitude. This means if we double the amplitude of a wave, we would have 4 times the intensity, or 4 times the rate of energy transfer. Trebling the amplitude would give 9 times the intensity, and so on. If we plotted a graph of intensity against amplitude squared, it would give us a straight line through the origin. Now to look at how the intensity of a wave reduces as we move away from a point source. Here we have a sphere, the area of a sphere being given by the formula 4 pi r squared. If we imagine a point source of power P at the centre of the sphere, radiating energy equally in all directions, we'll consider a small section of that moving out to the right. If we move a distance r from the point source, we can mark out a square through which all the radiation leaving in this direction must pass. If we say the square has area A, moving twice that distance, 2r from the point source, drawing a similar square, this now has 4 times the area of the first one. Therefore the intensity at this point must be a quarter what it was at this point. Moving a distance 3r from the point and drawing yet another square, this now has an area 9a. Therefore the intensity here is 1/9 what it is here. Intensity is given by the formula power divided by area. The power we said was P, and as all the energy must pass through the surface of the sphere of area 4 pi r squared, the area must be 4 pi r squared, giving intensity I is equal to P over 4 pi r squared. As intensity is power in watts divided by area in square meters, it will have the units of watts per square meter. Now to look at the phase of a wave. Here we have a wave and another wave, and the two are lined up, so peak meets peak, trough meets trough. They would add to give a wave of twice the amplitude. This wave is not in line with this wave. Now peak meets trough, trough meets peak. They would add to give a straight line. They completely cancel each other out. We say that these waves are in phase, whereas these waves are completely out of phase. Anywhere between the two situations is possible.